In this video, I'd like to go through some of the molarity practice problems that we didn't have a chance to go through in class. So we're going to start with some basic molarity problems where we just look at using molarity to determine things like how much mass we need to make a solution or what the concentration of a solution is. So we started with problem number 2 in class, and I'm going to do problems 1 and 3 just to show you guys a little bit of extra, a few different ways of doing this. So for the first one, it says that 0.0678 grams of NaCl is placed in a 25 milliliter volumetric flask. The salt is dissolved in water and the flask is filled to the mark. Calculate the molarity. So if we remember from class, molarity is equal to the moles of NaCl divided by the volume of the solution. So in this case, our solution volume is 25 milliliters. So if you convert that, if we do a rough conversion of 25.0 milliliters to liters, we divide this by 1,000 milliliters for every 1 liter. This is going to give us 0.0250 liters. So what it's basically saying is if we take this 0.0678 grams of NaCl and we put it into 25 mils of solution, inside of a volumetric flask, that basically is a flask that you fill up and it gives you a certain amount of volume. So we have the bottom part already, 0.0250 liters. So now what we need is the top, which is the number of moles. And to do that, we're going to take our 0.0678 grams of NaCl, and to get the number of moles, we're going to divide by the molecular weight. So the molecular weight of NaCl is 58.44 grams for every 1 mole. And in this case, our number of moles is going to be 0.001160 moles of NaCl. So we can put that over here, 0.001160 moles, and we get our concentration when we divide of 0.00464 molar. So that's how you work with concentration. So remember, basically units of concentration, so I'm just going to write it, I'm going to cross this guy out because we're not going to do that. So we did number 2 in class, but the main thing with concentration is that it's another unit conversion that allows us to go to moles. So we have our molecular weight, which allows us to go from mass to moles. We have Avogadro's number, which allows us to go from number of particles to moles. And we have our new thing, which is volume of a solution. And in this case, we can use the concentration in molarity. Okay? So molarity is equal to moles per liter. It's just another unit conversion. So let's look at the third one. In this case, it says how many milliliters of a 0.163 molar solution of NaCl would be required to give 0.0958 grams of NaCl, and I give the molecular weight of 58.43 grams. So in this case, what we're doing is following our little diagram here. They give us a mass of NaCl, and we're going to go from mass to moles. And then using the moles, we're going to figure out the volume. So it's going to be a 3-stepper. So to do this, we're going to start with our 0.0958 grams of NaCl. And when we multiply this, we have to get it to moles. So we're going to divide by the molecular weight, which is 58.43 grams for every 1 mole. And then once we have the number of moles of NaCl, we can now invoke the concentration. So the way to think about concentration in this case is that our 0.163 molar is the same thing as 0.163 moles per every 1 liter. So we can then write in our unit conversion 0.163 moles for every 1 liter. And now the question asks us for milliliters, so our last step is going to be for every 1 liter, there is 1,000 milliliters. So in this case, when you do the math out, what you're going to wind up getting is 10.05 milliliters. And if we do significant figures, we have 3 significant figures there, and we have 3 significant figures there, so we're going to have 3 significant figures over there. Okay? So those are the iterations of working with molarity. We saw one in class where it asks us how many grams would we need to make a certain solution. And then we can also figure out what the concentration is if we take a certain amount of mass and dissolve it in a certain amount of water. That's problem number 1. And then we can see the other case where we have a certain type of solution and we want to know how much of that solution we would need in order to get a volume. How much volume of a solution we would need in order to get a certain mass. So now the second type of problem we talked about in class was dilution calculations. And the operative thing to remember with dilution calculations, so I'm going to kind of start off just reminding you guys, is when you do a dilution, we're going to take a flask, and in this flask, let's say that we have 1 mole in 1 liter. Okay, so this is going to equal 1 molar. Now, when you do a dilution, you're diluting it, meaning you're adding more water. So let's say that we have the second flask where we fill it up a little bit more. So we fill it up twice as much. In this case, we're now going to have a volume of 2 liters. But what's interesting is that the number of moles haven't changed. We haven't added or taken out anything from the flask. So we now still have our 1 mole for every 2 liters. So this is going to give us 0.5 molar. So the link when you're doing a dilution is that the number of moles stay constant. And I showed you guys in class that when we have this circumstance, we can use this equation where it's M1 times V1 is equal to M2 V2. And in this case, M is the molarity, V is the volume in liters. And we can use this to our advantage. It's a simple equation for doing dilution problems. The operative thing with this, though, is that the number of moles stay the same because we're just adding water or just changing the volume. So let's look at the problem number 3. So in this case, we take 80 mils of a 6 molar solution. So we're going to draw a little line here. And we're going to draw our solution 1. So here's solution 1. And we've got 80 mils of a 6 molar solution of NaOH. And we're going to dilute this to solution number 2. We're going to add to it 880 mils. So in the flask, we have our 80 mils that was there originally, plus 880 mils, which is going to equal 960 mils total after we do the dilution. So we're going to have more in the flask now. So the reason why I'm adding the 2 is because we're taking the 80 mils and we're adding 880 mils to it. So V2 in this case is going to equal 960 mils, whereas V1 was going to equal 80 mils. So M1 is equal to 6.0 molar. So now the question is what is molarity 2? So we're going to set up our M1 V1 equals M2 V2. And for this, we're going to have our information from the first one, which is 6.0 molar. And we're going to convert 80 mils into liters. So this is going to be 0.080 liters when we convert this to liters. If you divide by 1,000. Same thing here. This is going to be 0.960 liters if you do the math and divide by 1,000. So we have 0.080 liters over here. This is going to equal M2, which is what we're trying to solve for, times 0.960 liters over there. So now if we solve for M2 in this case, our concentration will be, let me just look at my work in the problem, it should be 0.50 molar. So that's if you take the 6 times 0.080 and then divide it by 0.960. So M2 in this case is going to be 0.50 molar. So remember, with dilution problems, the tell in these problems is that you're taking a certain solution, typically it'll be a volume and a concentration, and then you're doing something to that solution where you're changing the volume. The big thing with dilution calculations is typically these are a change in volume. So the two iterations could be either you take a solution and you add liquid to it, or you put it into a larger volume. That's this particular case. Or it could say how much of a certain solution would you need to put into another solution with a larger volume to get a certain concentration. So you're either calculating a volume or a molarity. So that's how we deal with the dilution calculations. Remember back to class, what gravimetric analysis is we're looking at getting information about a ion in solution. So if we have a solution, for example, in this case, we have a sample of limestone that contains mostly calcium carbonate. There's calcium carbonate and other stuff. And we want to know how much calcium is inside of a sample of limestone. So they take a sample of limestone that's 128.3 milligrams. They dissolve it in HCl. So when we do that, we're going to have calcium 2 plus dissolved in a solution. And with gravimetric analysis, we precipitate this to make a solid, and from the solid, we get information about the amount of calcium that was originally present in the sample. So if we read this question, and that goes for any gravimetric analysis problem, the tell for a gravimetric analysis is you have some kind of ion in solution or some kind of unknown sample. You precipitate the ion out of solution with something, in this case it's oxalate, and then from that precipitate, from the mass of precipitate, we're going to backtrack to get information about the ion. So we're going to get we can get the number of moles of the precipitate, and then built into the number of moles of precipitate, we'll have the number of moles of that ion. So in this case, we take 128.3 milligrams of limestone. We dissolve it in HCl according to reaction 1. So they're taking the calcium carbonate, dissolving it in HCl and making calcium chloride. And then going back, we then take the calcium chloride and we precipitate that as calcium oxalate into solution. So that's basically what we're doing. Now the fact that we have two reactions here just means that we can use the stoichiometry going across. So whatever came out of the first reaction is going to go into the second reaction, and so on and so forth. So whatever calcium chloride we make from the first reaction is going to go into the second reaction. So we'll look at that in a second. Now, the end of the question says, calculate the percentage of calcium in the limestone. So if 142.2 milligrams of precipitate is formed. So we're making 140.2 milligrams of the calcium oxalate, and we're starting with 128.3 milligrams of our original sample, which is a mix of calcium carbonate and other stuff. So so our job is to figure out how much calcium carbonate was originally in that. Now, if we remember percent composition, so the percent of calcium in the limestone is going to equal the mass of the calcium divided by the total mass. So in this case, multiplied by 100. So in this case, our total mass is the 128.3 milligrams of the limestone that's being dissolved. So, and then what we want to figure out is how much calcium was in that limestone. That's what we're going to get. And the way that we're going to get that is by looking at the calcium oxalate that was precipitated. So we get 140.2 milligrams of the calcium oxalate, C2O4, and built into this precipitate is the fact that for every 1 mole of CaC2O4, that's going to equal 1 mole of calcium. So for this particular problem, we're going to be using this precipitate to get information about the amount of calcium that's in the calcium oxalate. So if we can get to the number of moles of the calcium oxalate, we can then get to the number of moles of calcium. So to get to the number of moles of calcium oxalate, we're going to divide this by 1,000 first, because there's 1,000 milligrams for every 1 gram. We can't use the molecular weight until we divide by the until we get it into grams. Then we need to invoke the molecular weight. So in this case, the molecular weight of the calcium oxalate is 128.10 grams of calcium oxalate for every 1 mole. This is 128 of CaC2O4. Now, inside of that, for every 1 mole of CaC2O4, there's 1 mole of calcium. So in this case, this is giving us information about the calcium, because we know that for every 1 mole of the full compound, there's 1 mole of calcium. So then with this, we're going to multiply for every 1 mole of calcium, there's 40.08 grams of calcium. That's the molecular weight of calcium. And then because up here we have our answer in milligrams, we're just going to do a quick conversion of this to milligrams. For every 1 gram, there's 1,000 milligrams. So when you do the math out, you're going to get 43.86 milligrams of calcium that was in the original sample. So we can plug that in over here. So 43.86 milligrams. Multiply this by 100, and we're going to get our 34.19% for the calcium and the calcium oxalate, for the calcium in the limestone. So again, with the gravimetric analysis problems, we're taking an ion or an unknown solid. We're releasing the ion into solution, possibly by dissolving it, or in this case we dissolve it with HCl. And then we are getting information about that ion by precipitating it out with something else. So that's how you're going to do it. Now in this case, it looks like everything was relatively easy, because there was a lot of one-to-one stoichiometry. There was 1 mole of calcium inside the calcium oxalate, which makes life a lot easier. But if this had been something like Fe2O3 or let's say BaCl2, where there's not necessarily a one-to-one stoichiometry, for example, with the chloride, then you would need to have whatever the mole ratio is here accurately represent what's inside. So for example, like I was saying, with Fe2O3, if this were the case, for every 1 mole of Fe2O3, that's going to equal 2 moles of iron. So, just keep that in mind when you're doing this. So the next problem we're going to look at is a volumetric analysis problem. And really, this is just a fancy way of saying stoichiometry with solutions. So in this case, what we're going to have to use our conversion here. So for moles of A, we can either come into this using the molecular weight, which is going to allow us to go from mass to moles, or our new addition to this spoke is going to be our molarity, which is in moles per liter, where we can go from a volume of a solution to the moles of A. Then, using stoichiometry, we can go from moles of A to moles of B and come out either with a mass from the molecular weight or with the volume of a solution using the molarity of B. So that's exactly what we're going to do in this problem. They give us the volume of a solution and its concentration of the sodium phosphate. So this is going to be one of our reagents. And then they're asking us, well, how much of another reagent would we need in order to react with that? And they give us the molarity. So in essence, we're starting with sodium phosphate, a volume of it, and we're going to go to moles of sodium phosphate, and then using our stoichiometric ratios to go to moles of nickel sulfate, and then finally to volume of nickel sulfate. So that's how this problem works. In essence, we're getting information about one in order to get information about the other. This is exactly like we did in Chapter 3. In Chapter 3, we would say, here's a mass of one thing. How much of a mass of another would we need to get? Now, instead of it being a mass, we're just using volume. And you could start with a mass and end with a volume. You could start with a volume and end with a mass. It doesn't make a difference. As long as you can get to moles, either from the molecular weight or the molarity, you can go to the other reagent and get whatever you would need, either mass or volume, as long as you have either the molecular weight or the molarity of the other thing. So let's start this problem off by first taking our 45.7 mils of the sodium phosphate. We have to convert this to liters because if we remember, there's 1,000 milliliters for every 1 liter. This is essentially equivalent to 0.265 moles for every 1 liter. That's what molarity is. So it's a unit of concentration telling us how much is in the solution. Once we're in liters, now we can bring our concentration in. So we know that for every 1 liter, there is 0.265 moles of the sodium phosphate. And once we're in moles of sodium phosphate, we can use our coefficients. So for every 2 moles of sodium phosphate, there are 3 moles of nickel sulfate. And so now we've gone from A to B using our stoichiometric coefficients. And we know from our concentration there are 0.375 moles for every 1 liter. So we can say that for every 0.375 moles of the nickel sulfate, we're going to have 1 liter of that solution. So now the last step is to get this into milliliters because that's what the problem asks for. So we're going to convert liters to milliliters. And when you do all the math out, the final answer for this should be 48.4 mLs. So in essence, what we're doing is we're going from a volume to a number of moles. This is using the molarity. Then we're using our stoichiometric coefficients to get to from moles of A to moles of B. And then finally, we're going from moles of B to a volume of B using the molarity again. So that's the idea. And in this case, this is just pure stoichiometry, except the input is a volume. The conversion factor is a unit of concentration, molarity. And again, I'm coming out the other side. We're using the molarity to get us to a volume. Now, we could have put a mass on the left side or a mass on the other side. It just depends on what the problem is looking for. You can handle it simply by following this chart. So that's how you do volumetric analysis problems. And what you're going to find is that titrations are the same thing as volumetric analysis. The only thing is that titrations just so happen to focus on acids and bases, whereas volumetric analysis is for any reactant. It's a more general term. So in our final problem, we're going to take a look at a titration problem. Titrations are very similar to volumetric analysis. The only concept that we have to really add is this idea of an endpoint. And what that means is that basically that's when you reach stoichiometric equivalence. It's also sometimes referred to as the equivalence point. So, for example, in this problem, we have a vinegar solution that contains acetic acid and water. We don't know how much acetic acid. And we're titrating a sample where we have 5 grams of this vinegar solution, and we're going to react it with a known. So in this case, the known is a solution of sodium hydroxide that we know the exact concentration of. It's 0.108 molar. And we're going to look to see when we get to stoichiometric equivalence, where the acid in the unknown has been fully reacted. The way that these are typically done is you have what's called a burette, which is this instrument that we use in lab. It basically is a graduated tube with a valve on the end of it, and it allows you to add very controlled amounts of an acid or base solution into a solution that you want to test, into an analyte solution. So inside the burette, you'll have some volume, and then you look to see how the volume changes when you reach the endpoint. Now, the way that you tell that there's an endpoint, because you couldn't, with like an acid-base reaction, for example, there's no color change. So you have to add something to it. And normally what you'll have is in your analyte solution, you'll have some kind of indicator. So an indicator could be like universal indicator, bromothymol blue. They have a whole bunch of different ones. And what that means is when you get to pH 7, the color will change. So it'll turn, for example, with phenolphthalein, when you're adding a base, when it goes through the equivalence point, it'll turn pink. And then you'll know that you've reached the equivalence point where the moles of acid have been fully reacted by the base. And then you get there. So that's why we use the indicator. That tells us we've reached the so-called endpoint. Now, it's important to realize that at the endpoint, this is when you reach what's called stoichiometric equivalence. So in this case, we have acetic acid and sodium hydroxide. So that's a 1-to-1 mole ratio. If, for example, we had barium hydroxide instead of sodium hydroxide, well, then there's going to be a 2-to-1 ratio. So you're going to need 2 times the acetic acids for every 1 barium hydroxide, because inside of barium hydroxide there's 2 hydroxide ions. So we're not necessarily talking about equivalence in terms of the moles equaling each other, although in this case that is the case. The moles of acetic acid will equal the moles of OH minus. They are equaling each other, but taking into consideration the stoichiometric coefficients, if there are any. So in this case, it's just 1-to-1. So let's look at how to work this problem. So just like we did on the last problem, this is just like the volumetric analysis problem. Basically, they give us the volume of the NaOH and the concentration of NaOH, and they want us to calculate the mass percentage of acetic acid. So on the other side of this problem, we're going to have the molecular weight. So to give you kind of a feel, what we're doing here is we need to get the mass percent of acetic acid in the vinegar. So we need to get the mass of acetic acid. I'm just going to summarize that as AA over the total mass times 100. So that's how you do a mass percent. So in this case, that's going to equal, our total mass is 5.00 grams of the vinegar. We need to get the mass of the acetic acid, and when we multiply that by 100, we'll have our final answer. So to get the mass of acetic acid, we're going to have to use this information from the titration. So to kind of give a schematic in this case, we have for our moles of A, which is the sodium hydroxide in this case, they're giving us information in terms of the volume of the solution, and they give us the molarity. Then we're going to use our stoichiometric coefficients, the mole ratio of A to B, and we're going to use that to get to moles of B. And what's interesting in this case is we're actually not going to come out with a concentration. What we're going to do is we're actually going to come out with a mass of acetic acid, and we're going to use the molecular weight. Now, the reason why we're getting the mass is because we're looking for a mass percent of acetic acid in the original solution. Theoretically, this could ask you what was the concentration of acetic acid in the water, but I'm kind of just showing this as another example of how you can handle anything as long as you understand that the spokes coming out from moles will allow you to convert to either mass or volume using that either the molecular weight or the concentration. So let's set this one up. So we have 39.1 mils of NaOH. And of course, the first thing we're always going to do is we're going to convert this to liters, because our concentration in this case is 0.108 moles for every 1 liter. So that, again, that concentration, that molar concentration, tells you how much stuff you have per given liter of solution. So now we can just write, for every 1 liter of solution, we have 0.108 moles of NaOH. Now we're going to do some stoichiometry. It says that we need this 39.1 mils of the 0.108 molar solution to reach the endpoint. So at the endpoint in this case, we know that there is going to be, for every 1 mole of NaOH, we get 1 mole of the acetic acid, which is the CH3COOH. And for our final step, we're going to go to a mass. So we need to say for every 1 mole of the CH3COOH, we have 60.05 grams. And that's coming from the molecular weight, which is right there. So what we've done is we've come into this with the volume to get the number of moles. Now, since we're at the end point, this tells us that we've reached stoichiometric equivalence. So we know that since we have a 1-to-1 ratio, our moles of the NaOH are going to equal our moles of the acetic acid. That's what the endpoint tells us. So we can use our stoichiometric coefficients to convert from one to the other, because we know that we've reached the point where they're equivalent. And then finally, we're going to come out of this with our 60.05 grams per mole to give us the mass of acetic acid. So when you do the math in this case, you should get 0.2535 grams. So let me just draw an arrow. 0.2535 grams of the CH3COOH. And we're going to plug that in up here, 0.2535 grams. And we can do our division. So when you divide 0.2535, keeping in mind that our significant figures are going to be at 3, we get a final percent of 5.07%. So that should be our final answer, is 5.07%, which actually makes sense because vinegar is a 5% solution of acetic acid in water. That's the stuff that you buy in the supermarket. So just like the volumetric analysis, we're using our understanding of stoichiometry to get information back about a solution. The thing that distinguishes a titration is we're specifically adding a solution that we know the concentration of to a solution that we don't know the concentration of or information about, in order to determine information from the analyte solution or the solution we don't know about. So, and that's exactly what we did here. We add this standardized base solution. We wait to see when the indicator changes so that we can tell that we've reached the endpoint. And from there, we can go back and extract out the information about the acetic acid. In this particular case, it asked us to do the mass percent, but you could have also done a concentration by taking the moles of the acetic acid and dividing by the volume of the solution, for example. So that's sort of all of the different types of problems that you might see. The important thing, as always, is to practice these. And there's a bunch of practice in the back of the textbook, and there's a bunch of practice in the online drills.